Hi, Dr. Ward here. This is the final video in our series on dimensional analysis. In the earlier videos, we went through step by step, starting with math concepts that underlie dimensional analysis, some 1- and 2-step dimensional analysis problems, then longer multi-step problems and problems that involve derived units that have different units on the top and the bottom. And then finally, we covered cubed and squared units. In this video, we're just going to go through several examples that involve different combinations of all of those factors. So let's start with a fairly straightforward dimensional analysis problem, which is how many grams of gold are there in 0.67 moles of gold? Okay, so in order to solve a dimensional analysis problem, you need a conversion factor. There is a direct conversion between moles and grams of gold. And if you're not familiar with this concept, it involves the periodic table and something called the molar mass, which you can certainly check on. But what we know is that 1 mole of gold has a mass of 197 grams. So 1 mole is equal to 197 grams. We don't have 1 mole, we have 0.67 grams. So how would we convert that? We multiply times the conversion factor. 1 mole goes on the bottom because we're going to cancel that out. On the top goes our grams, 197 grams. We're going to end up with a unit of grams. That's what we want. And it comes out to 131.99 grams, or rounding to the right number of significant figures, that would be 132 grams of gold. Okay. So that's a 1-step problem, fairly straightforward. We have a direct conversion from moles to grams, so we just needed the 1 conversion factor. So let's take a look at another problem. All right, so here's another simple 1-step problem. The question is, if I have 125 grams of aluminum, how many milliliters? What would the volume of that aluminum be? In order to solve this, we need a conversion factor with grams and milliliters. That refers to a property called density. The density of aluminum is 2.7 grams per milliliter. So anytime you have a conversion factor that has the 2 units involved, the unit you're starting with and the unit you're ending with, that's going to be a 1-step conversion. All right, so let's set this up. We're going to take our given 125 grams, and if you want to put that over 1 to keep track of your numerator and denominator, that's not an issue. And then we're going to multiply it by our conversion factor. We have 1 milliliter equal to 2.7 grams. We're going to put the 2.7 grams on the bottom because we want that grams unit to cancel out, which means we're going to have our 1 milliliter on the top. And when we do that out, 125 times 1 over 2.7, our unit's going to be milliliters. And it comes out to 46.3 milliliters of aluminum. All right, so let's take a look at a 2-step problem. So we're going to find out how many atoms of carbon are there in 24.02 grams of carbon. That's how many atoms. Okay, so we saw in an earlier problem that we can convert from grams to moles. There is no single conversion factor between grams and atoms, because atoms of different elements have different masses. So we can't just convert between grams and atoms with a single conversion factor. But there is a conversion factor that we can use. Or there's actually 2, which is why this is going to be a 2-step problem. We can convert grams of carbon to moles of carbon. Okay, that's molar mass. Again, that would be using the periodic table. That's a different concept that would be in a different video. And then we can convert moles of carbon to atoms of carbon. Okay, so 1 mole of any element equals 6.02 times 10 to the 23rd atoms of that element. And that could be molecules. The term mole is just a number, like a dozen. It means a specific number of things. In this case, that number is 6.02 times 10 to the 23rd. Again, that's a topic for another video. But we're going to use that as a conversion factor in this problem. So we're going to start with 24.02 grams of carbon multiplied by our first conversion factor. We're going to convert grams into moles. 12.01 grams of carbon equals 1 mole of carbon. That's going to convert grams into moles. And then our second step, 1 mole of carbon is 6.02 times 10 to the 23rd atoms of carbon. It's that number of atoms of anything equals 1 mole. But for this purpose, we're going to have grams that cancels grams. We're going to have moles that cancels moles. We're left with our unit of atoms. And 24.02 divided by 12.01 times 6.02 times 10 to the 23rd comes out to 1.204 times 10 to the 24th atoms of carbon. Okay, so we had to have 2 steps here because there was no single conversion from grams to atoms, but we had 2 conversions, and we used the term mole, or the value mole or unit mole, as a bridge between grams and atoms. So that is often what happens. We can't get straight from one unit to the other, but by using these intermediate units where there's something in common, we can create a 2-step conversion in this case, or a multi-step conversion, which we'll get into here in a minute. So let's take a look at another problem. All right, let's take a look at another problem that involves a couple steps. Let's say we have a neon sign with a volume of 1,870 milliliters. So there's 1,870 milliliters of neon inside this tube that makes up the sign. And we know that the density of neon gas at this particular temperature and pressure is 0.9 grams per liter. The question is, how many pounds of neon are there in that sign? All right, so we've got the number of milliliters, we've got a density which has grams and liters in it, we want pounds, so we need a couple other things here. We need to convert grams to pounds, and we need to convert milliliters to liters, so we're going to need a couple of conversion factors here that we don't have yet. The conversion from milliliters to liters is that 1 liter equals 1,000 milliliters. And the conversion from grams to pounds is 1 pound equals 454 grams. So if we set this up, again, we're going to need a couple of steps here. We have our starting point, which is the 1,870 milliliters of neon. First, let's convert our milliliters to liters, and we're going to use the conversion factor of 1,000 milliliters is 1 liter. And then we have our liters and grams, our density here, and we know that 1 liter of neon has a mass of 0.9 grams. That's the density, 0.9 grams per liter. And then we want to convert our grams into pounds. So 454 grams equals 1 pound. Okay, so we needed 3 steps to get from milliliters of gas to pounds of gas. And if we check our units here, the milliliters are in the numerator of the first fraction here, so that cancels the milliliters in the denominator. Liters and liters, grams and grams, which means our final unit over here is going to be pounds, which is what we wanted. That was the question that we started with. So we're going to multiply all the numbers in the numerator, all the numbers in the denominator, and when we do all that out and we divide, we get 0.0037707 pounds. Since we started with 4 significant figures, that was the number of significant figures I left here, and we could convert that to scientific notation, which would be 3.707 times 10 to the negative 3rd power, and the unit here is pounds. So depending on whether you need your answer in scientific notation or not, those are the same number written in 2 different forms. So we've converted our milliliters of neon to pounds using the intermediate steps of grams per liter, liters per milliliter, and grams per pound. So a 3-step conversion there. 3 steps. Okay, let's take a look at another problem that's going to take us a few steps to get through. And again, sneaking in a little extra topic here, this is actually going to be a stoichiometry problem. If that's not something you're familiar with, you will get to it later. But when you do get to stoichiometry, might help to keep in mind that it's really just another type of dimensional analysis problem. So let's take a look at this. I've got a chemical equation up here. This is the reaction of propane and oxygen. It produces carbon dioxide and water. So it's the combustion of propane gas. So we want to know if I burn or combust, react 72 grams of oxygen, how many liters of CO2 would that produce? Okay, so we're assuming that we're going to react all the oxygen we have. There's a concept called limiting reactant that you'll learn about later if you haven't already, but we're not going to worry about that right now. We're just going to assume that we're reacting all of this oxygen, we're producing as much CO2 as possible, and we want to figure out what's the volume of that gas when we get there. So the first thing we need to do is figure out what's the conversion from O2 to CO2. Well, there's no one step to do that, especially we're also going from grams to liters, so there's going to be a couple of different steps involved, and this involves a chemical reaction that has its own conversion factors going on. So let's take a look at the O2 first. Whenever you're converting and involving things like grams and liters and chemical reactions, everything kind of goes through the center, which is moles. So we're going to have a conversion factor of 1 mole of O2 gas has a mass of 32 grams. We're also going to have a volume and a mole conversion for CO2. 1 mole of CO2 under what are called standard conditions has a volume of 22.4 liters. So we need that conversion factor. The other conversion we need is, since we're talking about a reaction, think of this like a recipe. What the chemical equation tells us is what is the ratio of oxygen to carbon dioxide in this equation. And when we look at the equation, we look at these numbers here, these big numbers called coefficients. And in your head, it might be helpful just to remember that this, you could read this as 5 moles of oxygen produces 3 moles of CO2, assuming everything else works out as it should. So according to the equation, the ratio is 5 moles of O2 to 3 moles of CO2. Okay, so we've got a bunch of different things going on here. We're going to set this up step by step, convert from grams of O2 to liters of CO2 using this chemical equation as our recipe and all the conversions that that's going to entail. So let's start with our 72 grams of O2. We're going to convert the grams of O2 to moles of O2. So 32 grams of O2 is 1 mole of O2. So we've converted grams into moles of O2. Next, using the equation, we're going to convert moles of O2 to moles of CO2. Here's our conversion factor there. It's also called the mole ratio. And it's 3 moles of CO2 for every 5 moles of O2. Now we do have moles on the top and the bottom of this conversion factor, which might be a little confusing at first, but keep in mind this is moles of CO2 and this is moles of O2. So they're two different substances that we're talking about here. And then we're going to convert our moles of CO2 to liters of CO2. Okay, so we have grams of O2 and grams of O2. We have moles of O2 and moles of O2. We have moles of CO2 and moles of CO2. So when we get all this together, what we're left with is liters of CO2. So we're going to multiply 72 times 1 times 3 times 22.4. That's going to get divided by 32 times 5 times 1. I almost forgot, if you want to put that 1 over there, keep your numerator and denominator in check. We're going to do all that math out, and when we come to the end of it, we end up with 30.45 liters of CO2. I started with a number that had 2 significant figures, so I would actually round this to 30 liters of CO2 for my final answer. All right, let's take a look at a couple more problems that are a little more complex even than this, and then we will wrap up our tutorials on dimensional analysis. All right, so let's take a look at a problem that involves a few different things. It's a little more complicated. We're going to throw in some squared units. We're going to throw in multiple steps. So let's take a look at if we have an object that is falling for 2.3 minutes. Let's assume it starts from zero, no velocity, and it falls for 2.3 minutes under the force of gravity. How fast is it traveling in miles per hour after 2.3 minutes? Okay, so we need to know a few things here. What's the acceleration of gravity? Well, that's 9.8 meters per second squared. There's our squared unit. We need to know minutes. We're going to convert that into seconds. We're going to convert that into hours. We know that there are 60 seconds in a minute and 60 minutes in an hour. And we know that there are 1,000 meters in a kilometer, and that 1.61 kilometers equals 1 mile. And it's probably worth pointing out at this point, we've been using all sorts of different conversion factors and things. Many of these you will be given as either part of your reference sheet or part of the problem for some of these less common conversions. Some you may be required to know, like meters to kilometers and things like that, the metric system. But don't worry so much about knowing all these conversion factors. You will either be given them or you will need to memorize some of them, depending on the situation. But mostly we're worried about how we set up and solve these dimensional analysis problems more than how we know the conversion factors. So let's take a look at setting this up. So we're starting with the time, which is 2.3 minutes. And again, if you want to put that over 1 to keep track of your numerator and denominator. Now, my acceleration is in seconds, so I know I'm going to need to convert minutes to seconds. I'm later going to need to convert it to hours, but I have all these units for time in there. So let's take a look at 9.8 meters per second squared. I've got my time in minutes, but I want to convert that to seconds. 1 minute is 60 seconds. Okay, so now it's in at least the common unit with the acceleration, and we'll worry about how to get to hours later. 9.8 meters per second squared, so that's 1 second squared, which, remember, squared units really just means the unit times itself, so it's seconds, right? Seconds times seconds. So the unit I have here for seconds is going to cancel out one of those. So in order to cancel out that other unit of seconds, I'm going to have my conversion of 60 seconds to 1 minute again. Now, I had minutes canceled out, so I'm introducing another unit of minutes here, which means I'm going to need to cancel that out again. But that's okay, as we'll see in a second, because I'm going to convert my minutes to hours. Okay, so I needed to get into hours eventually for my final answer of miles per hour. So all I did there was take advantage of that fact and the fact that I have my squared unit down here. Remember, seconds times seconds is seconds squared, or s squared. Now I've got hours, all of that converted to hours, which is what I want for the end. And then I need to convert meters into miles. So first I'm going to convert meters to kilometers. And then I'm going to convert kilometers to miles. And I ran myself out of room here, so I'm going to move down. So all of that equals 3,024 miles per hour. So minutes and minutes cancel out. Seconds here cancels out one of these. The other one gets canceled out here. Minutes cancels minutes. Hours stays, so that's where I have this in my answer. And then meters goes back and cancels out this meters. Kilometers cancels out this kilometers. I'm left with miles in my numerator. I'm left with hours in my denominator, so I end up with 3,024 miles per hour. All right, let's take another look at a problem that involves, this one is a cubed unit. It's going to take us a few steps to get through this. We're going to figure out if a substance has a density of 0.000287 pounds per cubic inch, what does that come out to in grams per milliliter? So these are both density units. Any unit that has mass on the top and volume on the bottom can be a density unit. So we're going to go from pounds per cubic inch to grams per milliliter. let's see what we need. We need to convert our pounds into grams. So 454 grams equals 1 pound. And then we'll convert our inches into centimeters. So 1 inch is 2.54 centimeters. And we'll deal with the cubed inches and the cubed centimeters in a minute. And then we're finally going to convert cubic centimeters into milliliters. And it's conveniently that 1 cubic centimeter equals 1 milliliter. Those two units are interchangeable in terms of their size. So we're going to start with our 0.000287 pounds per cubic inch. Remember that anytime you have a squared or cubed unit, it just means the unit times itself, or in this case, the unit times itself, and then times itself again. Cubic inches is just inches times inches times inches. So we're going to convert those when we get to it. But first we're going to convert our pounds to grams. So we have 1 pound is 454 grams. Okay, so that's actually all we need to take care of for the numerator. The denominator is a little more complicated because of the cube unit and because we're going from inches to milliliters, cubic inches to milliliters. So we're first going to take an intermediate step and we're going to convert 1 inch to 2.54 centimeters. Since we have inches 3 times, we have to convert it 3 times. Okay, and when we do that, so now what we'll have is we'll actually have centimeters times centimeters times centimeters in our denominator here, which is cubic centimeters. And then over here, we had 1 cubic centimeter. So again, remember, cubic centimeter just means centimeter times itself again equals 1 milliliter. So it took us a few steps to get there, but we're now converting pounds to grams, and then we're converting inches to centimeters, and then we're converting centimeters, cubic centimeters, to milliliters. Okay, so we've canceled out the pounds in the numerator, converted it to grams. We've converted the cubic inches first into cubic centimeters and then the cubic centimeters into milliliters, which that by itself is a pretty simple conversion because it's a 1-to-1 ratio. And when we do all that out, we get I'm going to move this down here, 0.00795 grams per milliliter as our final answer. If we wanted to put that into scientific notation, it would be 7.95 times 10 to the -3rd grams per milliliter. Okay, so cubic centimeters become milliliters, grams per milliliter. Put that in scientific notation, and we converted our pounds per cubic inch into grams per milliliter. All right, so this is the last one. I'm going to throw a whole bunch of stuff in here, and I'm not embarrassed to say I'm going to be checking my note card for this one just to make sure I keep track of all the steps myself. I'm first going to start by putting the problem up here for you to read because it's pretty detailed, so here we go. If the density of a neutron star is 10 billion tons per cubic inch, and we need to ship a 5 cubic centimeter sample to the Large Hadron Collider in Switzerland, it costs 1.25 Swiss francs per gram for shipping. How much will it cost in US dollars if the exchange rate is 1 Swiss franc for 1.11 US dollars? All right, let's take a look. So if we've got 5 cubic centimeters of our sample, and we said that a neutron star has a density of 10 billion tons per cubic inch, and it's $1.11 is 1 Swiss franc. How much would it cost to ship this? So let's set it up. So we're going to start with 5 cubic centimeters, remembering that it's centimeters, centimeters, centimeters. Okay, that's all going to be over 1. Then I'm going to convert my centimeters to cubic inches, cubic centimeters to cubic inches. Remembering that it's 2.54 centimeters is 1 inch, and I'm going to do that 3 times. Okay, so I've converted my cubic centimeters to cubic inches. And we said that the density was 10, I'm going to put this as billion tons, just to save space, per cubic inch, per 1 cubic inch. Remember, that's inch times inch times inch. All right, and the cost is 1.25 Swiss francs per gram. Okay, so we have grams in there. We need to convert our, we have to convert our grams to pounds. And then we're going to convert tons to pounds. So 2,000 pounds per ton. And we also need to convert our Swiss francs to US dollars. So $1.11 for every 1 Swiss franc. Okay, let's take a look at this and see if I did get this all right. Centimeters, 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 inches, 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 tons, tons, Swiss francs and Swiss francs, grams and grams, pounds and pounds. Canceled out all of my units except dollars. I want to know how much it's going to cost. So this all equals, put it up here, 5 times 1 times 1 times 1 times 10 billion times 1.25 times 454 times 2,000 times 1.11. That all is your numerator. The denominator is 2.54 times 2.54 times 2.54 times 1 times 1 times 1 times 1 times 1. So 2.54 cubed is your denominator. When you do that out, ready? It is 3809 407 225 113,662. So that's thousands, hundred thousands, millions, billions, trillions, quadrillions. It's a whole lot. If we put that into scientific notation, and since we started with one figure over here, it would actually all get rounded out to 4 times 10 to the 15th US dollars. Or roughly what Jeff Bezos earned in the time it took me to make this video. So it costs a lot to ship a neutron star, if you could do that. All right, so this was a very lengthy, complicated conversion. But again, all of these steps are things that we've gone over. We had our cubed units here and here. We had multiple steps to get from cubic centimeters to cubic inches, dollars to Swiss francs, tons to pounds, grams to pounds. Throw all that together. It's just a step-by-step process and making sure that all the units that you want to cancel out get canceled out. The only unit that was left at the end was the dollars, which is what we want our answer to be. So that means we set it up correctly. Obviously, there's the math involved in multiplying all these things across, multiplying the denominators, and doing the division correctly and keeping track of all that. If any of this didn't make sense, you can certainly go back and watch the earlier videos where we covered a lot of these step-by-step similar problems. This is a tough one, okay, and it was meant to be as the last problem. So that's our tutorial on dimensional analysis. Thanks for watching.